How to choose the right chemical indicator for titration. Title: How to choose the right chemical indicator for titration. Introduction. Titration is a widely used analytical technique that involves the gradual addition of a standard solution to a sample solution until the reaction between the two is considered complete. This process is essential in many scientific fields, such as chemistry, biochemistry, and environmental science, to determine the concentration of a particular species in a solution. Chemical indicators play a crucial role in titration, as they help identify the endpoint, where the reaction is considered complete. This article aims to guide you through the process of selecting the right chemical indicator for our titration. Understanding chemical indicators. Chemical indicators are substances that undergo a noticeable change in color or physical property when the solution's pH reaches a certain value. The change in color is indicative of the endpoint in a titration reaction, providing a visual signal to the analyst. Selecting the appropriate indicator greatly influences the accuracy and reliability of the titration results. Consideration factors. When choosing a chemical indicator for titration, several factors need to be taken into account. 1. Reaction type. Understanding the nature of the titration reaction is key to selecting the right indicator. Different reactions require different indicators. For example, acid-base titrations use indicators that change color around a specific pH range. Redox titrations, on the other hand, may require indicators that are sensitive to changes in the oxidation state. 2. pH range. Identifying the expected pH range of your titration is crucial. The chosen indicator should undergo a noticeable color change close to this pH range, enabling an accurate detection of TH. Endpoint. It is essential to select an indicator whose pH range coincides with the expected pH change of the reaction being analyzed. 3. Color change. A clear and distinct color change is vital in accurately determining the endpoint. The indicator's color in the acidic or basic form should be easily distinguishable from the intermediate color formed at the endpoint. The change should be sharp, sudden, and easily visible. 4. Sensitivity. The indicator's sensitivity to small changes in pH is crucial for accurate titration. If an indicator changes color over a large pH range, the endpoint might be harder to detect precisely. Therefore, it is important to match the sensitivity of the indicator to the expected pH change during titration. Common chemical indicators. A variety of chemical indicators are available, and some commonly used ones are discussed below. 1. Phenolphthalein. This indicator is colorless in acidic solutions and turns pink in basic solutions. It is frequently used in acid-base titrations when the endpoint lies in the pH range of 8.2 to 10. 2. Methyl orange. Methyl orange changes from red to yellow as the solution's pH increases. Its transition range lies around 3.1 to 4.4 pH units, making it suitable for moderately acidic solutions. 3. Bromothymol blue. This indicator exhibits a color change from yellow to blue, making it ideal for detecting pH changes in the range of 6.0 to 7.6. Bromothymol blue is often used in weak acid strong B. OSA titrations. 4. Potassium permanganate. In redox titrations, potassium permanganate is commonly used as an indicator. It changes color from purple to colorless as it gets reduced during the reaction. 5. Starch. Starch acts as an indicator in iodometric reactions by forming a deep blue color with iodine. It is used in the presence of iodine and is particularly useful in estimating the concentration and of reducing agents. Experimental pretesting. To ensure the appropriate indicator is selected, it is recommended to perform pre-tests. These tests involve conducting small-scale trial titrations using different indicators and establishing their suitability for the specific reaction. By performing these tests, you can observe the color changes and overall clarity of the endpoint. Remember to record the results for future reference. Safety considerations. While selecting a chemical indicator, it is essential to consider safety aspects. Some indicators may pose risks due to their toxic nature or the reagents used alongside them. Ensure proper safety measures and precautions are in place before selecting and using any chemical indicators. Selecting the appropriate chemical indicator for titration is crucial in obtaining accurate and reliable results. It involves understanding the reaction type, determining the pH range, considering TH, color change, and assessing the sensitivity of the indicator. By taking these factors into account and performing pre-tests, you can confidently choose the right chemical indicator for your titrati. On analysis. Additionally, it is important to prioritize safety and follow necessary precautions when working with chemical indicators. With proper consideration and experimentation, you can ensure success of your experiments and achieve accurate results. However, selecting the appropriate chemical indicator for titration can be a complex process. It requires a thorough understanding of the reaction being analyzed, the expected pH range, and the characteristics of different indicators. It is always recommended to consult literature and seek expert advice if needed. Furthermore, it is important to note that the selection of a chemical indicator is not the only determinant of the accuracy and reliability of titration results. Factors such as precise measurement techniques, proper calibration of equipment, and careful execution of the titration procedure also play significant roles in obtaining reliable data. In summary, choosing the right chemical indicator for titration is a crucial step in obtaining accurate and reliable results. Additionally, maintaining safety and following proper precautions is essential throughout the entire process. With careful consideration and attention to detail, scientists can enhance the precision and validity of their titration experiments. Continuing from the previous content. However, it is important to note that the selection of a chemical indicator is not the only factor that affects the accuracy and reliability of titration results. Other variables, such as the purity of the solutions, the temperature, and the presence of interfering substances, must also be considered and controlled to ensure precise and dependable results. Another consideration to keep in mind is the availability and cost of the chemical indicator. Some indicators may be expensive or difficult to obtain, especially in large quantities. Researchers must evaluate the practicality and feasibility of using a specific indicator based on their resources and budget constraints. These systems eliminate the need for chemical indicators, as they rely on the measurement of physical properties, such as conductivity or pH. While these automated systems offer increased accuracy and reproducibility, they may not be accessible or cost-effective for all laboratories or applications. Additionally, it is important to mention that titration is not limited to just acid-base or redox reactions. There are various other types of titrations, such as complex symmetric titrations, precipitate ion titrations, and argentometric titrations, each requiring a specific set of indicators and considerations. Complexometric titrations involve the formation of complex compounds between a metal ion and a ligand. In these cases, indicators that undergo a color change upon complex formation, such as metallic chromic indicators, are commonly used. Examples of metallochromic indicators include ureochrom black tea, muroxide, and chalcon carboxylic acid. Precipitation titrations involve the formation of a precipitate through the reaction between two solutions. The endpoint in these titrations is determined by the presence or absence of the precipitate. Indicators such as Moore's salt, ammonium iron 2, sulfate, or silver nitrate are used to detect the formation of a precipitate. Argentometric titrations, also known as silver titrations, involve the use of silver ions to determine the concentration of a species in a solution. Complexometric indicators, such as fluorescein or xylenol orange, are often used in these titrations.